All right, we are going to do structure and properties of carboxylic acids. So one of the main features of the carboxylic acids is, of course, they're acidic. They have a pKa of about, 4.5 or something. The pKa of acetic acid is 4.75. But let's talk about the structure a little bit. Now, it turns out that something like acetic acid is water soluble, and that's because you have a hydrogen bond acceptor and a hydrogen bond donor in the same molecule, and you have an OH bond. So this molecule here, if we draw it interacting with several water molecules, okay, can perform hydrogen bonding to the hydrogen of a water molecule. And it's got two lone pairs, so it could potentially do that to two water molecules. And then we have two lone pairs on this oxygen atom. So it can hydrogen bond interact with a water molecule, and it can hydrogen bond interact with another water molecule, and then has an OH. And that can interact with the lone pairs on a water molecule. So carboxylic acids that have 4 or fewer carbon atoms are going to be water soluble. So formic acid, acetic acid, propanoic acid, and benzoic acid are all very readily water soluble. Now, the interesting thing also is that things like acetic acid are completely miscible and soluble with benzene. Now, benzene is a completely nonpolar solvent, so it seems somewhat surprising that acetic acid, which is strongly hydrogen bonding and very polar because of all these electronegative oxygen atoms, would be completely soluble and easily mixed with something completely nonpolar like benzene. Why is that? Well, it turns out that acetic acid can hide its polarity or mask it in a sense by internally hydrogen bonding with another acetic acid molecule like this. So if these two carboxylic acids come together like this, the lone pairs on this oxygen can hydrogen bond to the hydrogen there, and the lone pairs on this carbonyl oxygen can hydrogen bond. And so it's kind of hydrogen bonding to itself, and the result is that you have nonpolar kind of stuff sticking off the sides, which is then interacting with benzene through just van der Waals forces. Okay, so it turns out that the intramolecular hydrogen bonding of carboxylic acids is so strong that when you vaporize, volatilize, or boil acetic acid, for example, you can actually detect the dimers in the gas phase. Okay, so it readily dimerizes. Okay, and again, this is through hydrogen bonding. Okay. Because acetic acid has such a high hydrogen bonding and polarity content, it has a much higher boiling point than things like ethanol, which only has a small limited amount of hydrogen bonding. Okay, so that kind of gives you an idea of its boiling points compared to alcohols. Okay, so carboxylic acids have a higher boiling point. Benzoic acid, for example, is a solid at room temperature, but the corresponding alcohol, which would be benzyl alcohol, is a liquid at room temperature. Okay, let's talk a little bit about the acidity. Now, when you have a carboxylic acid, this can readily react with sodium hydroxide. To give you the corresponding conjugate base. Now, this is a carboxylate, and it's resonance stabilized. Okay, so if you add sodium hydroxide to that, you get a salt. Okay, this is called sodium carboxylate, and it's a salt. Okay, Now, carboxylic acids are extremely acidic, or much more acidic than an alcohol, because of resonance stabilization, okay? So a carboxylate, remember we've talked about this before. Okay, so this is what we call a carboxylate. It's not a carboxylic acid because it doesn't have the OH, it's a carboxylate. And so this is resonance stabilized. The resonance structure is something we call equivalent in terms of types and number of bonds. So it's particularly stable, okay? And so the resonance stabilization of carboxylates is extremely strong, okay? And remember, again, negative charge, electrons like to spread out. They don't like to just sit on one atom. And so if you can smear them out through different resonance structures, it stabilizes the molecule, okay? To name these, you take the carboxylic acid that you have, okay? And if you treat this with sodium hydroxide, for example, we just sometimes write ONA, but there's no oxygen-sodium bond per se. You know, it's just an ionic interaction. So we might draw something like that. Okay. So just keep that in the back of your mind there. But that's kind of like a short way we might draw it. So if we're starting with butanoic acid, okay. The way we name the carboxylates is by chopping off the OH and the acid, and we incorporate the counter ion first, okay? So we're going to name this sodium butan, so leave a space there. And then we're going to add the ending 08. Butan 08, all right? Another example would be benzoic acid. And if we treat this with sodium hydroxide, we will make sodium benzoate. If you're drinking soda right now, you might check the ingredients. Sodium benzoate is often added to Coke, Mountain Dew, stuff like that as a preservative. If you have potassium, for example, you'll make the potassium such and such 08. So here there's a methyl group. Okay, so I think it's good to slow down and show something a little more complicated. This is 2-methyl propanoic acid. Okay, and remember we're going to ditch the oic acid and just put 08 in there, okay? And we want to put potassium first in the name. So the structure we want to draw over here is this one with an OK kind of at the end. And we're going to name this potassium 2-methyl propanoate. Okay, propan, and then just add 08. One way to remember that the ic changes to 8 is with the phrase, ic, I ate some acid. And that's one of the things you may have memorized in general chemistry. If you have acetic acid, it becomes acetate when it's the conjugate base, okay? Sulfuric acid becomes sulfate. So ics become 8s. So anyway, same thing here. That's the basics of naming, drawing the benzoates, butanoates, and so on, the carboxylates, okay? So that's how you name carboxylates. They're named as kind of a derivative of a carboxylic acid. Now let's talk a little bit more about the acidity. The acidity can vary ever so slightly depending on the chain length and the type of thing you have. But the two main things here are that if you have a carboxylic acid like this, okay, and you create the carboxylate, the acidity of the original starting carboxylic acid is influenced depending on the group that you have attached to the aromatic ring. If you have electron withdrawing groups, electron withdrawing groups through inductive or even resonance effects will stabilize that negative charge and cause the carboxylic acid to be more acidic, okay? So if the product is lower in energy, more stable, the starting material, relatively speaking, is higher in energy. So it makes it more acidic, okay? Now, you might review chapter 19 when we talked about electrophilic aromatic substitution. There are lists of electron withdrawing groups and which ones are strong electron withdrawing groups, which ones are medium, and which ones are weak electron withdrawing groups, okay? If the substance is an electron donating group, electron donating groups are listed in chapter 19 as very strong, moderate, or weak electron donating groups, like things like methyl groups or hydroxyl groups or amino groups, things like that. It's going to make the corresponding carboxylic acid less acidic, okay? So these are for benzoic acid derivatives, okay? That's the first thing. The second thing are inductive effects, okay? And this is something we talked way about in chapter 3 or 2, whichever chapter it was, when we talked about acidity. Okay. Rule number 1 is if you have an electronegative atom, it's an electron withdrawing group, because if it's electronegativity, it's going to stabilize the conjugate base. It's going to make the corresponding carboxylic acid more acidic. So the first thing is that if you have an electronegative element closer to your acidic functional group, it's going to have a greater influence, okay? So you're going to have more acidic on the right, less acidic on the left, okay? The analogy I used back in chapter 2 was if you have a vacuum cleaner, it's going to work better if you're right on the dust bunny than if you're kind of farther away, okay? So the chlorine that's further away is not really going to affect the acidity of the functional group carboxylic acid very much, okay? So that's rule number 1. And so I'm reviewing chapter 2 right now. You could probably just skip the rest of the video if you know this stuff. Number 2, okay, the more electronegative elements are going to have more dramatic effects. So remember, your periodic table kind of looks like this in the halogen group. Okay, you have fluorine at the top, you have iodine at the bottom. And so if we want to compare acetic acid, derivatives, okay, and I had 3 different halogens on here, okay. We're going to have more acidic to the right because fluorine is a more electronegative atom. It's more inductively pulling on the electrons and therefore stabilizing the carboxylate even more, making the carboxylic acid more acidic. Okay. The vacuum analogy is that the fluorine is like a really powerful vacuum, brand new from the store. It's got the clean filters and everything. It's very powerful to pull suction, whereas bromine is not really that electronegative. It's on the bottom of the table. Remember, more electronegativity increases going up the periodic table, and so this is like a very weak vacuum. It barely works at all. It's got a clogged filter, and it doesn't have much influence on stabilizing electrons. Okay, so that's rule number 2. Rule number 3. Has to do with the number of halogens you have. Okay. So if we have chloroacetic acid, dichloroacetic acid, and trichloroacetic acid, trichloroacetic acid is going to be more acidic because you have 3 electronegative chlorines all influencing the acidity of the carboxylic acid. Okay, so review chapter 2, which discusses acidity and inductive effects in much greater detail, but I just wanted to give you a brief heads up here. Okay, I'm not going to go through the Henderson-Hasselbalch equation and pH calculations. That's something that you probably did in 2nd semester general chemistry. All right, let's do a practice problem just to see if we understand these concepts well. Okay, I'm a very visual person, and I like to draw these molecules out. So let's do part A here and draw them out and see what we have here. And we want to rank each set of compounds in order of increasing acidity. So I'm going to label it most acidic and least acidic, and the one that I don't label is going to be in between the two. Okay? So butyric acid is 4 carbons. I would have liked to name it butanoic acid, but sometimes things are named with a Y there. So butyric acid has 4 carbons. And we've got 2 halogens. We've got 2 chlorine groups, one at carbon 2 and one at 4. And the other one has 2 and 3. And the other one has methyl groups at 3 and 4. I think that's a mislabeled I think that's a mislabeled substance, because if you put a methyl group at carbon 4, then you don't have a butyric acid anymore. You have a pentanoic acid. But anyway, let's just analyze these structures here. This problem looks a little weird to me. But let's look at the electronegative halogens first. That's what you want to focus on. So this guy here has 2 halogens that are closer to the carboxylic acid functional group than these 2. Okay? The chlorine at carbon 4 is further away than chlorine carbon 3. So this is going to be the most acidic. Okay? Now you want to carefully think about how do halogens compare to a methyl group. Okay? So remember that a methyl group, we said, was weakly electron donating. It's a weak donor, a weak electron donating group when we talked about in chapter 19. So that has the opposite effect of acidity, okay? Chlorines will withdraw electrons, stabilize the carboxylic acid, and make it more acidic, whereas electron donating groups will donate electrons in and anger the carboxylate and destabilize it. It'll make the carboxylic acid more shy to jump in the swimming pool and lose that proton, okay? So this is going to be least acidic here. Okay? And remember, electron donating groups do the opposite as electron withdrawing groups, okay? In part B, let's draw these structures here. We have propionic acid, which is 5 carbons. So 1, 2, 3. 3 is going to be a bromine group. 2,2-dipropanoic acid. And then 3,3-dipropanoic acid. Okay, so you want to look at location as well as number. So first of all, we're not comparing bromine with chlorine or anything like that. We're still dealing with a 5-carbon chain carboxylic acid. So the only difference is the number of halogens and their location. Okay, so first we look at location. Okay, location is very important. Okay, so if we look at the middle molecule here, the 2 halogens are closer to the carboxylic acid. That's going to have the greatest influence, and that's going to make this guy here the most acidic. Okay? Next, we compare these 2 molecules, and we can see that they both have the same locations. They're at carbon number 3. But this carbon with 2 bromines is going to be more acidic than the one with 1 bromine. Okay? Remember, 2 vacuum cleaners are better at stabilizing the carboxylate than 1. So this is going to be the least acidic. Okay? 1 halogen is not going to stabilize as well as 2 halogens. Okay? And 2 halogens closer to the carboxylic acid is going to stabilize the most. Okay? So that's section 9. A lot of students don't have too much trouble with this. If you're taking my class, do not worry about grabbing your calculator and trying to figure out how to calculate pH for any of these. Okay? Just know more acidic, less acidic, and be able to name carboxylates. Thanks for watching, and check out my other videos. And give a like, give a thumbs up, please subscribe.